7a, confidence intervals for a population mean where you have a large sample or the population standard deviation is known. Now, this is the point in statistics where we start doing inferential statistics, meaning that we take information from a sample and we project it onto the population. So what we're going to deal with here with confidence intervals, we're going to start out with something very simple, which is called a point estimate. A point estimate is a single point or single value that is an estimate of what we expect to happen in the population. So basically we use the sample to find a value that we think reasonably represents what the population is doing. So when we do that, in this case, we're dealing with confidence intervals for a population mean, meaning that, remember, a population mean, that's the average of the population, all items of interest. We tend to deal with samples, and you have sample means. So the point estimate for a population mean is a sample mean. So we take x bar, and we say, well, x bar is approximately equal to mu, our population mean. So our sample mean is a good estimate of the population mean. So if I have a set of data points, 17, 21, 22, 19, 25, then I can find the sample mean. In this case, I have 1, 2, 3, 4, 5 data values, so n is equal to 5. The sample mean, x bar is equal to, grab the calculator. All right, sample mean is equal to the sum of all these, 17 plus 21 plus 22 plus 19 plus 25, which gives us 104. We divide it by the sample size 5, gives us 20.8. So our sample mean of 20.8 says that the distribution that these data values came from, we would estimate that the population mean is about 20.8. Now, it's a relatively safe assumption that the population mean is not exactly 20.8. I'm just going to put approximately equal to mu, right? The idea of a point estimate is it's a single point that is a reasonable guess as to what the population parameter would be for that. But we should realize that that's not going to be exact. If I grab 5 random data values, it's not likely that's going to actually give me the real population mean. But it gives me a start. And what we're looking for with confidence intervals is that we're now going to not only have a point estimate, but we're going to create an interval, which is a range of values that we say is likely to give us an estimation of our population mean. And how we do that is, if we're creating a confidence interval, and I'm going to use CI for confidence interval, for a population mean, let me put 4 as opposed to just putting mu there, then we can do that by taking the point estimate x bar and subtracting E, which I'm going to define E as the margin of error. Margin of error, that gives us a range, a little bit of leeway in our numbers. From x bar minus E to x bar plus E, our margin of error. And this is going to create a confidence interval. We get the sample mean, and then we add and subtract some value to give us a buffer, or to create this interval. So if we said that we were doing this with a margin of error of 3, so if we said in this case that E was equal to 3, then our confidence interval for mu would be 20.8 minus 3 to 20.8 plus 3, so that's 17.8. Sorry, yep, 17.8 to 23.8. And that would be our confidence interval for our population mean. So we start with a point estimate, and then we add and subtract some margin of error to give us a confidence interval. Now, unfortunately, it's not that quick and easy. We have to do a little more than just having some E. We have to find E. And E comes from a relatively simple equation. E is equal to Z sub 0 times sigma over the square root of n. So Z sub 0, or actually Z sub C, we would use in this case, because we're going to call Z sub C the critical value. Okay, so Z sub C times sigma over the square root of n. Well, where do these things come from? What is this? Okay, well, first of all, n, that should be pretty straightforward. N is going to come from our sample size. So we've got that. Sigma, well, there's two things that can happen. One, sigma is known. We have the population standard deviation already. The other possibility is we have a large sample. So what is a large sample? A large sample is when n is greater than or equal to 30. So if we have a sample that is greater than or equal to 30, then that's considered to be a large sample. If we have a large sample, then we can say that the sample, actually I'll put that there, but if we have a large sample, then we can say that our sample standard deviation is approximately equal to our population standard deviation. So large sample, we can use the sample standard deviation in place of sigma, the population standard deviation. If we know what sigma is, what our population standard deviation is, we can plug that in. So that leaves the only thing left is, where does this Z sub C come from, this critical value? And that comes from our confidence level. So a confidence level. Anytime we're dealing with a confidence interval, we're going to have a confidence level. What is that? Think of it as the percent chance that we're right, or how likely we think we are to be right. So if I were to say that the average grade on the final exam is between 80 and 90, you go, okay, well, that's not too bad. But I say I'm only 50% sure of that. Now you start going, wait a second. If you're only 50% sure of that, then it may or may not be between 80 and 90. You really don't know. It's like, yeah, flip a coin. Heads, it's between 80 and 90. Tails, it's not. Right? So that would be considered a low confidence level. I'm only 50% confident in the interval that I give you. Whereas if I say I'm 99% confident, then that makes more sense. You go, oh, okay. 99% confident, we can work with that. That means he's pretty sure it's going to happen. So our confidence level is how confident we are. Well, that still doesn't tell us where this critical value Z sub C comes from. And let me make a little space here, and I'll do a drawing so we can see what we're going to do. So if we're dealing with a confidence interval, remember we're dealing with normal distributions, right? If I'm dealing with a confidence interval, basically I'm taking a chunk of this. And let's say I'm 90% confident. So 90% confidence level. So 90% confidence level. Then what I can say is 90% is in the inside of this interval of my normal distribution. If 90% is inside, then the other 10% is in those tails. Right? If 90% is in here, the other 10% is in those two. Because normal distributions are symmetric, if 10% is in the tails, that means 5% is in this tail, and 5% is in that tail. So half of our extra percentage here goes into each of those tails. It gets split up evenly. So now I've got 5% here, 90% here, and 5% here because I'm dealing with a 90% confidence level. Now what I can do is I can say those vertical lines represent our critical value z sub c. Z sub c and negative z sub c, right? They're going to be equal and opposite. So that means if I use the normal distribution table and do a reverse table lookup, if I've got 5% here, that's 0.0500. So I can look in the body of the table for the closest thing to 0.0500. And so I'm looking in the body of the table, and I see 0.0505, and I see 0.0495. So if I have those, the z-score associated with 0.0505, is the right spot again, is negative 1.64. The z-score associated with 0.0495, negative 1.65. Now when we're doing a reverse table lookup, we always look for which one's closer to the value we were looking for. We were looking for 0.0500. This one's 5 above, this one's 5 below, so they're equidistant. When they're equidistant, you average these two values, so I get z sub c, or negative z sub c, is equal to negative 1.645. And since z sub c is just the negation of that, that would be 1.645. So again, negative 1.645 and 1.645. So we looked and we found out what's the area in the tail. So we have our confidence level, that goes in the middle. Take whatever's left over, divide it evenly between the two tails. Find that area, do a reverse table lookup, which means we're looking in the body of the table for the closest value, then associating it with the z-score directly off the table. In this case, it was equidistant, so we took the average of those two z-scores, and we get z sub c. So now we have z sub c is equal to 1.645. Now, I'm going to let you in on a little secret. If you look in the bottom left-hand corner of the first page of this table, we see there's another little table here. You probably can't see it very clearly, but what this says is critical values, level of confidence, C, and it gives you confidence levels as decimals. I see 0.80, 0.90, 0.95, 0.98, 0.99, If we go to 0.90, a 90% confidence level, we see that Z sub C is 1.645. I don't know if I can get where you can see it or not. But if you look on your table, you'll be able to see that. So even though I used a reverse table lookup to get this, the standard confidence levels that we would use, 80%, 90%, 95%, 98%, 99%, there's that little table in the bottom left-hand corner that gives you the value. So we have a 90% confidence level, Z sub C is equal to 1.645. Once we have that, we can use the standard deviation in the sample size to find our margin of error. Once we have our margin of error, we can add and subtract that from the sample mean, and that will give us our confidence interval for our population mean. So I've gone through that. Let's give it a shot. So I'm going to erase everything that we've got here. And we're going to build a confidence level, a confidence interval, sorry. Just going to get that stuff out of the way. Okay, just remember that E is equal to Z sub C times sigma over the square root of n. All right, so let's say that we have the following set of data. Or actually, I'm not even going to do a set of data. I'm going to give you the type of information that I would give you on a question. You want to find a 95% confidence interval, CI, confidence interval, for the population mean, or we can say for the average age of MVCC instructors. For the average age of MVCC instructors. So you take a sample of 12 instructors and find that their average age is 57.2. The population standard deviation is known to be 6.8. Let's find the 95% confidence interval for the population mean. Now I said we took a sample of 12 professors. The average age of that sample is 57.2, and I said the population standard deviation is known to be 6.8. Remember, we either need a large sample where x is greater than or equal to 30, or we need to know the population standard deviation. We said it was known, so boom, we have 6.8. Realize that I could have not given you that. I may have said you take a sample of 12 professors, find their average age to be 57.2 with a standard deviation of 6.8, and that would make this the sample standard deviation S. And we wouldn't be able to do this because we wouldn't have the population standard deviation, and we wouldn't have a large sample. So we wouldn't be able to do it. But in this case, the population standard deviation was known to be 6.8. So what are we going to do? We have our x bar. We need to find our margin of error. So E is equal to, well, if we're going to do that, we have sigma, we have n. What we don't have is Z sub C, the critical value. So if I've got a 95% confidence interval, I grab that table and I look at that bottom left-hand corner for 0.95, and I get Z sub C is equal to 1.96. Took it right off that little table in the bottom corner. So having that, I have Z sub C, I just need to find my margin of error. Z sub C is 1.96 times sigma, 6.8, divided by the square root of 12. So now I need to grab that calculator again. So 1.96 times 6.8 divided by the square root of 12 gives me 3.85. It actually gave me 3.84746, right number of other digits. I'm giving myself a couple decimal places. That's what I like to do. Also, notice that my sample mean was to 1 decimal place. I have a tendency to like to take my margin of error 1 decimal place more than whatever my point estimate is. So if I've got 57.2, that's to the 10th place, I like to take my margin of error to the 100th place. Just personal preference. You need to have at least as many decimal places in your margin of error as you have in your point estimate, but never have less. Don't make this 57.2 and then round this to 4. That would be very bad. Okay, so now we have our margin of error. Then I can start creating my interval. So I've got x bar 57.2 minus the margin of error 3.85. And 57.2 plus the margin of error, 3.85. So let's do this. So 57.2 minus 3.85 gives me 53.35. And then 57.2 plus 3.85 gives me 61.05. And we're almost done. The final thing we need to do is we need to label this as what it is. And this is a 95% confidence interval for mu, for our population mean. So we're 95% confident that the population mean will be between 53.35 and 61.05. And that's finding a confidence interval for a population mean. Now, notice that in this case, we knew the population standard deviation. Now, you may look at it and go, well, if we're trying to estimate the population mean, why would we have the population standard deviation? It seems it would be easier to know the population mean than to know the standard deviation. Well, that does seem true in many cases, but there are a number of things that come into play that. Maybe I'm trying to find the average age of professors this year. 10 years ago, and don't just say it's going to be 10 years older because people retire and new people come in. But maybe 10 years ago, we did this study at that point, and we know what the population standard deviation was of their ages back then. Because at that point, we looked at all the data and we found the population standard deviation. It would be a reasonable guess that the population standard deviation would be about the same now. So that's one way we could have it. Another way we may have it is, who knows, maybe someone gave it to us for some reason. Or maybe we're working on something that has a known standard deviation. IQs, we know the standard deviation for IQs in the population is 15. So if we were dealing with IQs at MVCC, then would it be reasonable to say, well, if the population standard deviation for IQs is 15, that at a school like this, where there's a large enough student body and enough people on campus, that the population standard deviation of the people at MVCC would resemble that of the population at large? So yes, there's a number of ways we can do that, but sometimes we don't have it. Sometimes all we have is a large sample. So let's do another example which allows us to work through this again, but where we don't know the population standard deviation, but we have a large enough sample that we can approximate it. So I'm going to get my calculator out of the way. erase this, pick up my eraser, which decided to do a header on me. I think it determined it was too painful going through this, so it just decided to take its own life and jump onto the floor. Okay, so we want to find the average grade on the final exam. And we want to find it at we'll go for a 98% confidence level. And I'm going to do CL. CI was confidence interval, CL confidence level. So at a 98% confidence level, we want to find the population mean, or the average grade on the final exam. So I can say for mu. So we take a sample of 42 exams, and we find an average grade of 72.6 with a standard deviation of 11.1. Now notice the wording on that. When we did the previous example, I said the population standard deviation was known to be. Here I said that we took a sample of 42 exams, we found the mean to be 72.6 with a standard deviation of 11.1. The only way I can tell you that we have the population standard deviation is to state population standard deviation is. I think there's only one time in my teaching career that I came up with a way that I was able to sneak it by without saying the word population related to standard deviation, still give someone a population standard deviation. So if you don't see population standard deviation is, you're probably dealing with a sample standard deviation. And especially if it's worded, you take a sample and find a mean of such and such with a standard deviation of such and such, that's tying that standard deviation to that sample. So we have a sample standard deviation. So one of the first things we're going to look at is the population standard deviation known? No, it is not. We have the sample standard deviation, but we do not know the population standard deviation. So then we look at, do we have a large sample? A large sample is greater than or equal to 30. 42 is greater than or equal to 30. So yes, we have a large sample. So we can use this. So 98% confidence level, we're going to look in that bottom corner of the table. 0.98 gives me 2.33. So I've got z sub c is equal to 2.33. It's so nice to be able to just look it up in that little corner of the table, rather than having to break it up. Because if I were to break it up, I'd have to do this, create my thing, say 98% is in here. That means 1% is here and 1% is there, which means I'm looking 0.0100. I'm looking for the closest thing that I can in the body of the table. And then I do a reverse table lookup and I get negative 2.33, and I realize this one's got to be positive 2.33, and I do all that work. So we can do it, but if we don't have to, why are we going to do that? Okay, so 2.33, that's our z sub c. We can find our margin of error. Margin of error is equal to z sub c, 2.33, times sigma. Well, we don't have sigma, but because we have a large sample, we can use the sample standard deviation s and say that's approximately equal to sigma, so 11.1. Over the square root of n is 42. Okay, so now we can find our margin of error. Grab that calculator again. So we have 2.33 times 11.1. Take the square root of 42 and divide that. And I get is equal to 3.99. So our margin of error is 3.99. Now that we have that, we can find our interval. X bar, 72.6, minus 3.99, That 3 looks really bad. And 72.6 plus 3.99. So 72.6 minus 3.99 gives me 68.61. And 72.6 plus 3.99 gives me 76.59. And then remember, the final step in this is we've got to state what it is. That is a 98% confidence interval for mu. We're 98% confident that the average grade on the final exam is between 68.61 and 76.59.